Good morning, Townview. Welcome back to Chemistry Online.
All right, so today we're going to be talking about the electromagnetic spectrum, also referred to as the EM spectrum. So top of your page, let's go ahead and write that down, the electromagnetic spectrum. So last time y'all were in here, we talked about the energy of electrons. We're going to talk about that just a little bit at the end of the class. All right, let's move on. So first, I'd like to see if y'all could identify the parts of the wave. Who can tell me what we call the highest point in a wave? All right, crest is correct. That's good. What do we call the lowest point? It starts with a T. What is it? All right, good, trough. What about this part right here? So the highest point to the origin. All right, that's amplitude. Good. Man, y'all remember this really good. And then this part right here, this is called the origin. And that's just where the wave begins. And then what do we call the distance from trough to trough or from crest to crest? All right, wavelength is correct. This is also the wave. So from this part of the origin to this part of the origin, that's one wavelength. And then here's another one. So in total, what you're looking at here is about 2.5 wavelengths. All right, let's move on. Don't worry about that. We already discussed these. Don't worry about these. All right, so let's talk about frequency real quick. So here at the top, I'm going to label this one A. I'll label this one B. So when we talk about frequency, we're just talking about how often something happens. In chemistry, when we talk about frequency, we're talking about the number of cycles that pass a given point in a given amount of time. When we're talking about frequency, we use the unit hertz, and hertz is just how many passes per second. So if something is 1 hertz, that means it's happening 1 time per second. What if something is 60 hertz? 60 times per second. What if something is 120 hertz? 120 times per second. So that's how frequency is measured. Now, looking over here, looking at A and looking at B, which one is more frequent, A or B? Which one has a higher frequency? A has a higher frequency. Which one has a longer wavelength? B has the longer wavelength. Good. So what you want to identify is if something has a longer wavelength, you're just going to have a lower frequency. All right, so next we have the EM spectrum. You don't need to write the electromagnetic spectrum as a series of waves that have different wavelengths. What I want you to do, though, is write this whole thing out. So I don't need your numbers, so you don't have to write any of the numbers. What I want to see are all these parts of the spectrum, so gamma, X-ray, ultraviolet. And then here at the bottom we have, one second, here at the bottom we have red, orange, yellow, green, blue, indigo, and then violet. I wouldn't just write the letter, I would write the entire color. So let's go ahead and do that. I want to see all of these on your page. I'm going to give you all a minute, 2 minutes actually, to get that done. Okay, so let's go ahead and go over these. So can anyone tell me what you guys know about gamma? What are gamma rays? Can anyone tell me who Bruce Banner is? Who is Bruce Banner? It's not Batman. Who is Bruce Banner? All right, and it is the Hulk. And what did the Hulk study? He studied gamma rays. So this is important because this is how I remember gamma rays. So Bruce Banner, who is the guy who turns into the Hulk, he studies gamma rays. And what do gamma rays do to him? They denature his DNA and they turn him into what he is. So Bruce Banner, he studies gamma rays. Gamma rays are extremely harmful. They denature your DNA. And what I want you to know, this we're going to label on our list. So this is going to be the strong side. So these are the strongest waves, the gamma rays. Anybody know some real life applications to gamma rays? Okay, so gamma rays are used to treat cancer. They're also used to sterilize some equipment. For example, if you're trying to send some equipment to the space station, you want to sanitize it. You don't want to send any bacteria up there. So they use gamma rays for things like that. But another thing to know about gamma rays is they're also cancer causing. So gamma rays are a byproduct of radioactive decay. So anytime you have material that's decaying, for example, uranium. So if you have uranium and it's decaying, you're getting some gamma rays out of that. So it's a product of radioactive decay, and it's cancer causing. All right, next up we got X-rays. Can anyone tell me some applications for X-rays? What are they good for? What are they used for? All right, so they're good at seeing your bones. So before we explain that, everybody look at my screen real quick. So why are plants green? All right, that's exactly what I wanted to hear. So they reflect green light. What do they absorb? All right, so they absorb all the other colors. So they reflect green, which means they absorb everything else. So your bones, so your body will absorb X-rays. However, your bones will reflect X-rays. That's why we can see your bones when we do X-rays. X-rays are also good at spotting pieces of metal. So when you're going through airport security, all your stuff goes through an X-ray because the metal will reflect X-rays. So there are a lot of applications to X-rays. But when you go to the dentist and they put the lead coat on you, why do they do that when they're about to use their X-rays? What are they trying to do? They're trying to protect your organs. Good. So X-rays are also cancer causing. So this causes cancer. This causes cancer. All right, next one we have is ultraviolet. Can anyone tell me what ultraviolet light is? What is the main source of ultraviolet light? All right, the sun. So the sun is what provides UV. That's where we get most of it. Can anyone think of some applications for ultraviolet? Okay, so the UV flashlights, sure. What's another application? How about y'all's nails? Why do y'all put them under UV? What does it do to the acrylic? It hardens the acrylic. If you've ever been to the dentist, they also use UV in your mouth. What do they use the UV for? What does it do to the fillings? It hardens the fillings. There are a lot of applications to UV. Anybody got a reptile? Nobody has a pet reptile? A bearded dragon, a snake, a python, a frog? No? All right, so cold-blooded animals, they need UV rays, keep them warm, keep their blood boiling. Any other applications? All right, so another application of UV is very often fruit, like strawberries, will go through UV. The reason for it is it'll kill the bacteria. So over here we have our goggles. Y'all have seen me use this thing with goggles. What does it mean when this happens? What does that sound mean? All right, it means that they're done. And what's happening is when I turn this on, it comes on a UV light. I can't show y'all the UV light. It turns off as soon as I open it. But it's a UV light that hits the goggles to sterilize it. So that's how we keep them clean and kill all the bacteria that's in there. So that's another use of UV. Any other uses for UV? Are we good? All right. So after UV, immediately after UV, what color do we get? What color do we get after UV? Violet. This is really important to know. So hands up if you remember Roy G. Biv. Roy G. Biv. All right, if you don't remember it, let's go ahead and write it down. Everybody real quick. Roy G. Biv. And this just tells you the colors in order. So we have red, orange, yellow, green, blue, indigo, and violet. In my scenario here, you can see that they're in reverse order. You could see this chart written either way. So it could start with the highest frequency to lowest frequency, or it could go lowest frequency to highest frequency. In this scenario, we're going high frequency to low frequency. But what you need to know is immediately after ultraviolet, you get violet. I'm not going to go over the colors. Y'all know the colors. But it goes from violet all the way to red. And then what comes immediately after red? What do we get after red? We get infrared. Can anyone tell me some uses for infrared? Infrarojo. Any uses for infrared? Nobody's ever used infrared? All right, y'all know how when you're like watching TV and then you put up the volume and nothing happens because the like remote is under the blanket? Has that ever happened to anybody? Like you got to take it out and you got to point it at the TV? Okay, so there are two types of remotes. There's the type of remote that requires that you point it and the type of remote that doesn't require that you point it. So if you look at my screen right over here, everybody see this thing? The little black thing right here? So that's a infrared sensor. On my remote is over here. So if your remote has one of these, that little clear thing right there, or the new ones are just going to have a black bar that goes all the way across. This is an infrared remote, and it sends a signal directly to this. These are the cheaper remotes. The more expensive remotes are the ones you don't have to point. What technology do those use? Anybody know? What is it? I think I heard it. What is it? Nope. So what technology do those use? Do you have to point your headphones at your phone? They use Bluetooth. So when you're using your Roku or you're using your Fire Stick, those run off Bluetooth, so those don't need to be pointed anywhere. And those are the more expensive remotes. So you could get an IR remote for like $10. The Bluetooth remotes, they're like $25, $30. All right, so that's infrared. Can anyone think of other uses for infrared? What is it? Well, that's just red light. All right, let me give you another example. Did I ever show you all the gas leak video? Anybody heard of the Caterpillar phone? Y'all never heard of the Caterpillar phone? Anybody know the company Caterpillar? All right, so here's the Caterpillar phone.
You through the many features of the app. Upon opening MyFLIR, you will be able to point the camera and instantly visualize temperature on the phone screen as a thermal image. Iron is the default palette, with hot being yellow and cold purple. You can change the palette options here for different situations. For example, if you wanted to simply see the hottest point in view, select the hottest palette.
Isn't that cool?
By selecting the mode button, you can take a photo, video, time-lapse, or broadcast alive.
If you're a plumber, if you're an electrician, stuff like this is extremely valuable. If you're a plumber, you also work with gas lines. And infrared or thermal cameras are really good at viewing gas leaks. Let me show you all a quick video of that. I can't tell you why this video exists, but man, is it useful. The arrow's just telling you where to look. Good. She just walked away from it. So I actually had this issue earlier this year. My gas line was leaking somewhere inside my house. I didn't know where it was leaking at. Eventually I found it, but if I had a thermal camera, it would have been real easy. You just open up the camera and it'll show you where the gas is coming out from. So if we had a gas leak in the room, the Caterpillar phone or just a thermal camera would allow us to very easily identify where the gas is coming from. So that's just another use for infrared. Any other thoughts, uses for infrared? No? All right. Go ahead.
Like the weather stuff, and like when they do the weather on the news and it shows like
So anytime you see thermal cameras, that's going to be infrared. All right, one other thing I forgot to mention back on the UV side is we didn't mention this, but UV is also cancer causing. So this side is the cancer causing side. Just know that about this side. We just talked about IR. Let's go ahead and move to radar. Can anyone tell me what radar is used for? All right, for radars. Not really for scales. Can anyone think of some uses for radar? Okay, that's sonar. Kind of like echolocation is what you're talking about. What about radar, specifically radar? What about airplanes? Do they use radar? Do airplanes use radar? What do y'all think? All right, so airplanes use radar. Has anyone ever been, well, y'all don't drive, but has anyone's parent ever been pulled over? I'm gonna draw this again. I'm gonna draw it like that. It's that cool new truck. All right, so you'll have a cop standing behind this thing. You know what I'm talking about? They're always standing behind something. And then you'd be driving, and then they shoot these radars at you, and then the radars are beamed back to their radar gun. And what are they able to do with that? They can find out how fast you're moving. So another use is in baseball. So they'll use these radar guns to figure out how fast the baseball is moving. So that's another use for radar. Any other uses for radar? All right, well, we can stop right there. That's fine with me. What about FM? Anybody here got an FM radio? Hands up if you've ever listened to FM radio. I know y'all Spotify people, but who listens to radio at some point in their life? All right, so has anyone listened to AM radio? What's on AM? All right, so there's a bunch of static. That's true. What else is on there, though? What is it? Old music? Okay, what else? All right, so I'm going to clear the page because we already wrote most of this down. We don't need any of that. So now we're talking about FM. So FM has a 1 meter wavelength. 1 meter wavelength on the board is about this big. So 1 meter, 3 feet. This is about 3 feet from here to here. So an FM wave is 1 meter. What about an AM wave? How big is an AM wave? What's 10 to the power of 4? What's 1 times 10 to the power of 4? All right, 10,000 is correct. So if an FM wave is 1 meter long, how many meters is an AM wave? 10,000 meters long. So let's say this is you, and you're at Townview and you're listening to your radio, and you're picking up AM radio waves. Let's say you pick up an entire AM wave, and I'm going to draw it this big. This is an AM wave. And an AM wave is 10,000 meters long. In the same time, how many FM waves could you pick up? In the same time you pick up one AM wave, how many FM waves could you pick up? 10,000 is correct. So for every one AM wave you pick up, you could pick up 10,000 FM waves. So when you're listening to FM radio, that's why you get the higher quality music. Your radio is picking up 10,000 packets of data for every one packet of AM data. But there is a difference in these. There is a difference in like their value. Who here has been to Houston with their family? How long between here and Houston does the radio work? Because I know your phones don't work and you got to listen to the radio. So how long until the phones to the radio stops working? All right, it's actually less than halfway. So the total distance. Anybody know how far from here to Houston? So some people say it's 3 hours, 30 minutes. I've never gotten there in less than 5. And I'm I'm hauling, you know? Yeah, that's how long it takes. All right. Well, I guess I'm coming from Fort Worth, so a little bit farther. Let's check the map. Before GPS, this is how we had to figure out how far things were. All right, so here it is. Welcome. All right, so it's about 250 miles. Some of y'all said halfway until the radio starts dying. Truth is, it goes out about Ennis. Anybody know how far from here to Ennis? All right, so it's about 35 miles. So when we talk about FM, FM has a band of about 70 miles across. So it'll go about 70 miles in a circle. That's about how far an FM wave can go. However, you get high quality audio. What about AM waves? How far do you think they go? All right, so they go significantly farther. They can go nationwide. So because it's a much longer wave, it can go cross country. FM waves, they just can't do that. So FM waves are much more localized. However, you get higher quality audio. Yes. So you get higher quality audio with FM. However, you get longer distance with AM. So each one's got its strength and its weakness. All right. Let's keep going. So TV, I'm not going to discuss TV. Y'all know TV. What about shortwave? Anybody know what shortwave is? So shortwave is going to be about where microwave is. It's also where police radios are, or truck driver radios. So truck drivers, these guys who drive like cross country, they're usually on the same road with the same truck drivers for a long period of time. So 100 miles, they're going down a highway, and all these trucks are they're moving in line with each other. So they'll get on their shortwave radio, and they'll just communicate with other people in line. So let's say one of them gets cut off by a blue BMW. What's going to happen? What are they going to do if they get cut off by a blue BMW? They're going to let everybody in line know. Have y'all seen that movie, Are We There Yet? Just like that. You know what I'm talking about? That's why you don't want to bother a truck driver. Any questions about the EM spectrum? Are we good? Yeah. That's a good question. Let's find out. So where on the spectrum would they be? All right, so those are going to be also infrared. So it's called near infrared, which is slightly, it's closer to the color part of the spectrum, but it's pretty close to infrared. So basically thermal. All right, let's keep going. So next up, we have the wave particle theory. So everybody in your journal, wave particle theory. And then I got a quick video I want y'all to watch before we write down our definition. You don't need to write any of this top stuff. This is the part I want you to write. But before you write that, I'm going to pull up a video real quick. This right here is the GOAT. Anybody know this man? Anybody know who this guy is? All right, there's a big picture of him outside of SEM. Y'all should go check it out. All right, I'm gonna play this video for y'all.
Scientists, in their never-ending fascination with light, set out to devise ways of isolating smaller and smaller units of it. It proved to be the passageway through the looking glass. It was the crossing of a threshold into a wonderland where the known rules of physics do not apply. For the first time, they were able to isolate the tiniest unit of light, a single photon. And to perform Young's double-slit experiment on a whole new level, tracing its precise path either through the right slit or the left slit. We'll pull over to the side of the road for the best possible view of which slit, the right or the left, the photon passes through to get to the far wall. Left slit, right slit, another right slit, left slit. If we watch them all day long, the pattern would be random. About half would go through either slit. Wait a second. Where are the waves? Where's Young's interference pattern? This is where the weird begins. I cannot explain to you what you're about to see. That's because no one on Earth understands it yet. If you can't live with that, then you're not going to be happy with what lies up ahead. On the smallest possible scale that we've ever discovered, the quantum universe, the mere act of observation changes reality. Okay, photons, keep on coming. This time, we promise not to look. You're not going to believe this, but we can change the pattern on the far wall simply by not watching which slit the photons pass through. I know it sounds crazy, but in every trial ever conducted, the outcome depends on whether or not the experiment was observed. So the reason we didn't get the interference pattern earlier wasn't because we chopped up the light into single photons. It was because we were observing which slit the photons passed through. But how could a photon know if someone is watching?
That's it. Y'all know how y'all act different if y'all on camera? Photons do the same thing. All right, so light acts like a wave when it travels, but it acts like a particle when it's absorbed. Go ahead and write that down, and then we'll discuss in a minute. All right, so here's the double slit experiment here. I'm just going to show y'all the experiment, except I'm just going to churn it. So let's say that it's the same experiment, except this time we're just turning it on its side. So if I had some sand, because sand is a particle, so I'm just going to go with sand. If I had a bucket of sand and I were to pour it over this. So here we have solid ground, and then over here we have our double slit. So here we have one, and then here we have our other one. If I were to pour the sand into here, how is it going to go? Is it just going to fill this bottom section like that? How's the sand going to fall in there? What's it going to do? Divide how? Okay, then what? How's it gonna land down here? What's it gonna look like? Is it gonna have a shape? What was that? All right, triangles is correct. So it's gonna look like this. It's gonna form two piles. So basically two little mountains. And the reason for that is because that's just how it falls. So think of it like an hourglass. So it's gonna fall in like an hourglass, and it's gonna form these two piles right here. So when light acts like a particle, basically when it's being watched, it acts like a particle, and that's what you're seeing right here. I'm going to zoom in so I get a better view. So you can see that in the center, it's much more, it's a lot darker, showing you that that's where it's most intense. Basically, that's the center of the pile. And then on the outsides, that's where it's less intense. Basically, the other part of the triangle. So this is how it acts when it's acting like a particle. Now, when it acts like a wave, this is what you end up seeing. And this is what happens when it's not being observed. So the observation part of this whole thing, that's the confusing part. So if we were to observe these particles, so let's say there was a light sensor in here that could see where the particles are going, then they act like particles. However, if we remove the sensor, so once the sensor is gone, they begin acting like waves. Any questions? I really can't explain it any better than that. That's the best I can do. When you get to physics, I'm pretty sure they can explain it better than I can, but we just got to talk about it with regard to electrons, yeah.
Don't like the lines when it's not being observed, like the most dense parts are when the position on the wave function is like the highest probability.
Yeah, so the center, that's where it's going to be the darkest. So the top of the pile, that's just the peak. That's going to be the darkest point. Any other questions on this, or are we good? All right, so let's go ahead, move on to our numbers. So now we got wave calculations. So luckily for you guys, we're not actually going to be solving these problems. I'm going to do some practice, but the expectation is you're able to do this. So we're just going to run through it, and then and really I want y'all to understand the trends, not really the calculating part. So looking at this, I just wanted to show you guys what it looks like on your formula sheet. Let me grab the formula sheet. So you don't need to memorize any of these formulas, but you do want to know where they're at. So all three formulas are right here on your periodic table. Very soon you're going to get this periodic table, which offers more information than the one y'all currently have. So let's go ahead and do some practice. So here's our equation. Who finished Unit 6? Hands up, you finished Unit 6 on positive chemistry. Okay, so you've already practiced this. So tell me, in math, I'm pretty sure someone in here knows this. So in math, when you have two things on the same side of the equal sign that you're comparing, what kind of relationship do they have? Is it a direct relationship or an inverse relationship? If they're on the same side, direct or inverse? Are you sure? All right, so what does a direct relationship mean? Say it again. All right, so that's correct. So direct means when one goes up, the other one goes up. So if they're on the same side of the equal sign, is that true? That when one goes up, the other goes up? Let's go ahead and do some practice. So instead of plugging in this whole equation, can y'all see this number? So C is a constant. It's the speed of light. And the speed of light is 3.0 times 10 to the power of 8. You don't have to write all that. So I'll be good with 3. So 3 is equal to 2x. So that's just this equation right here. 3 is equal to 2x. The 2 represents our frequency, and x represents our lambda, which is our wavelength. And then this is going to be our speed of light. So everybody grab your calculator. So 3 is equal to 2x. How do we solve for x here? We divide both sides by 2. The 2 goes away. And then it's just going to be x is equal to 3 divided by 2. So 3 divided by 2 equals what? A little bit louder? All right, 1.5. And then this is our x value, by the way. Let's go ahead and get the next one. So the next one is going to be 3 divided by 4. Or 3 is equal to 4x. I'll just rewrite the whole thing. 3 is equal to 4x. To solve this, we divide both sides by 4. 4 goes away. X is equal to what? All right, 0.75. And the next one, we're just going to replace the 4 with a 6. So, 1 second. So, 3 divided by 6 is equal to what? Point what? All right, 0.5. What were you saying? All right, click second and then mode, the button right next to second. All right, so so this is our frequency. As frequency goes up, and you can see that as we move downward, our frequency is going up. What's happening to our wavelength? It's going what? So as this one goes up, this one goes down. So what kind of relationship is this? This is a indirect relationship. So this part right here, if you want to write it, you can. If you don't want to write it, you don't have to. But this goes directly with the chart that you guys just drew. So let's take a look at this real quick. So here on the EM spectrum, I'm going to clear this. Where is the highest frequency? All right, gamma rays is correct. So here we have the highest frequency. And the reason we know this is where's the longest wave? AM. AM is the longest wave. And if the wave is longer, does it have a higher or lower frequency? So this is going to be the low frequency side. So this side is high frequency, this side is low frequency. And then with regard to wavelength, which one has the longest wavelength? All right, so here we have our longest wave. And then what about gamma? What's that going to be? That's our shortest wave. And then lastly, you guys are constantly being hit by AM radio waves. Are you constantly hit by gamma rays? No. Which one is more harmful? What do you think? Gamma is going to be the most harmful part. And we already talked about this, Bruce Banner. So here we have the strongest waves. The most powerful waves are over here. And then here we have the harmless waves. Another way to put it is highest energy. So here we have high energy. And then here we have low energy. All right, let's move on. Okay, so when frequency goes up, what does wavelength do? It goes down. When wavelength goes up, what does frequency do? It goes down. So an inverse relationship, just keep that in mind. So when they're on the same side of the equal sign and you have a constant on the other side, then it's going to be a inverse relationship. I'm going to give y'all a couple laps. I want y'all to try to solve this. I'm sure all of you can. So let's get... All right, so what's the answer y'all got? All right, a little bit louder. What is it? All right, I don't hear you. Got to be louder. All right, so the answer I got was 547,445. Hands up if you got this number. All right, so just about everybody got this. That's good. So, so to get the actual correct answer, we need to convert this to scientific notation, and we need to have the correct number of sig figs. So how many sig figs do we have here? How many do we have here? How many should our answer have? It should have 3. So we're going to put in our decimal, convert to scientific notation, 1, 2, 3, 4, 5. This gives us 5.47 times 10 to the power of what? And there's our answer right there. All right. All right, so let's go ahead and take a look at our equation here. So all we're doing is we want to isolate our lambda. And to do that, we're just going to divide both sides by 548. So then this goes away, and then wavelength is just equal to 3.0 times 10 to the power of 8 divided by 548. So there's a lot of ways to plug this into the calculator. The easiest way I know to plug it into the calculator is 3.0 e 8 divided by 548. This is the easiest way to plug it in, and you're going to get this answer. Now, you don't have to do it this way. Another way to do it, and this is the way most of my students choose to do it, is 3.0, so open parentheses, 3.0 times 10, caret 8, close parentheses, divided by 548. So this will get you to the same answer. I suggest doing it this way because this is just the way that I always solve things. But if you choose to use the E, you can do that too. Hands up if you use the E. All right, 2 of you? Okay, that's perfectly fine. So what's nice about the E is it doesn't require parentheses. That's the benefit of it. But if you choose to do it this way, this works perfectly fine. You just got to remember to plug in your parentheses. If you don't put in your parentheses, if you put in just this, very often you'll get to the wrong answer because of PEMDAS. Any questions? Did you get it? All right, so let's keep going. So over here we have examples of practice questions. I'm not going to make y'all do this. Most of y'all can solve these on your own. So here it says determine the frequency. If this is your wavelength, what is going to be our C value? 3.0 times 10 to the power of 8. It's a constant. And keep in mind it's going to be on your formula sheet. So you don't have to remember this number. It's going to be available to you whenever you need it. All right, let's keep going. So here it says the energy contained in a photon, a quantum, you don't need to write this, depends on the frequency. So I got 2 people here. I got this guy and I got this girl. Which one's got the higher frequency with regard to jumping rope? The girl has a higher frequency. Which one has higher energy? Does the guy have higher energy? That's sexist. Which one has higher energy? The girl. Why does she have higher energy? Because she's got a higher frequency. If we go back to this chart right here, we know that gamma rays have the highest frequency. They also have the highest energy. So this is just that. It's this trend right here. So when we look at this, the higher the frequency, the higher the energy. So this is going to be our energy equation. It's also listed in the same spot. So E is equal to HF. E is going to be your energy. H is going to be Planck's constant. Has anyone ever worked with Planck's constant? Hands up if you remember it from physics. All right, so this is Planck's constant, another constant, and this is it right here. So 6.63 times 10 to the power of minus 34. And then if you had to guess, what is F? Frequency. So let's go ahead and do these practice problems real quick. So you don't have to put in times 10 to the power of minus 34. We can ignore this part. Let's just do 6.63 divided by 2. So we're dividing by a frequency of 2. What is our energy going to be in that scenario? One more time. All right, 3.315. What about 6.63 divided by 4? 1.657. And then the last one. One more time. 1.105. So what's happening as our, hold on, are we solving this correctly? No, we're not. So our energy is what we're solving for. I said divide. We should be multiplying. All right, so I got to pause the video. I got to fix it. All right. All right, so here's what we should be doing. So we're still going to cross these out. You don't got to worry about these. But it's going to be 6.63 times 2, and that gives us our energy. So real quick, 6.63 times 2, what's that? 13 point what? 13.6. What about times 4? 26.5. And then what about the last one? 37 point what? All right, 0.78. And that's it. So as frequency goes up, what happens to energy? Also, it goes up. So here our constant is on this side, and then the two things we're looking at, they're on opposite sides. So what kind of relationship do we have in this scenario? This is going to be a direct relationship. Yeah. Any questions on this, or do we feel like we got it? All right, we're almost done. Let's go ahead and solve this one. Okay, so here's our last slide of the day. And this is all stuff that you've seen before. I just wanted to go over it one last time. So I'm gonna, let me fix this right quick. All right, so without looking at what it says here, what element is this? What element does that orbital diagram represent? All right, so these are two, by the way. Let's separate them. Let's look at this one. So what is that one? All right, beryllium is correct. What about this one? Is this one correct? No, it's not a correct notation. However, it is correct if we were talking about excited. Y'all remember excited? So what happens if you excite an electron? What does it do? It jumps to a higher energy level. In the case of beryllium, this electron jumped to that energy level. So if I were asking for a ground state, would this answer be correct? No, because that's not the ground state. It's an excited state. How do we identify the element? What do we got to count? We got to count the number of electrons. If it's got 4 electrons, it's going to be beryllium. Now, last thing I want to talk about is this GIF right here. So let's take a look at it. Wait. Okay. All right. So if you look at it like this, what element are we looking at right now? It's a hydrogen. That's right. And is it ground or excited? Right now it's a ground state hydrogen because it's got 1 electron on its first shell. So if we add energy to it just like this, what's going to happen? It's going to get excited and it's going to go to the higher energy level. Has it lit up yet? Yes or no? Has it produced light? Yes or no? No, it hasn't. That's the important thing to know. When does it produce light? When the electron goes back down. So right here, this is where it produces light. So when the electron jumps back to its ground level, it has to release that energy somehow, and it releases it in the form of a photon. So this right here is your photon. Any questions? Because that's it. That's all I got.
If you don't know how to do chemistry, hit that subscribe button. Let's go!